Welcome to this explainer. Today, we're diving into a structured masterclass on algorithm efficiency and the real-world trade-offs of sorting data. Whether you're managing a massive cloud database or just organizing a tiny list on your local machine, how you choose to sort fundamentally impacts processing speed and memory usage. So we're going to break down the science of making that exact choice. Here's our syllabus for today. We've got the math of growth, simple sorts, linear speed, the heavyweights, space trade-offs, and a final cheat sheet.
Let's kick things off with asymptotic analysis. This is how we judge an algorithm's speed mathematically, without getting bogged down by the specific coding language or hardware. It's purely about measuring how a function behaves as its input size approaches infinity. By looking at that rate of growth, we isolate the pure efficiency of the algorithm itself. It doesn't matter if it's running on a supercomputer or a 10-year-old laptop, we're looking at the underlying math.
Section 1. The math of algorithm growth.
To evaluate our sorting toolkit, we first have to understand the formal bounds of Big O notation. Let's translate this abstract math into something we all experience: commuting. Think of Big O as your worst-case commute traffic. It's an upper bound, guaranteeing your algorithm won't grow faster than a certain rate. Big Omega, that's your best case, empty highway. It's the lower bound, representing the absolute minimum time required. And finally, Big Theta is like a highly predictable train ride. It means the algorithm is bounded both above and below by the exact same function. It's a tight, precise bound.
As inputs grow, limits mathematically prove which functions dominate the others. This creates a strict dominance hierarchy of efficiency that really dictates our algorithm choices, from constant time on the far left all the way to factorial time on the right. This hierarchy is basically the ultimate cheat code for programmers. If you understand the scale, you can predict exactly how an algorithm is going to behave when you throw 1,000,000 or even 1,000,000,000 data points at it.
Now, by following 2 simple steps to handle constants, we learn exactly why we can just throw away minor terms like +100 and focus purely on the dominant growth rate. First, the sum rule tells us that if we have an equation like n squared plus n, the n squared eventually completely crushes the contribution of the smaller n, so we just drop the smaller term entirely. Second, the product rule tells us that nested complexities multiply. This is exactly why we focus on the turning point of data size. We ignore the small inputs and look strictly at those massive, dominant mathematical trends.
Section 2. Simple sorts for beginners.
All right, now that we have the math down, let's look at simple quadratic algorithms. As this quote brilliantly illustrates, these basic sorts scale terribly for big data. If you deploy an n-squared algorithm in a modern cloud environment with massive data, your processing time will skyrocket and it's literally going to cost you money. It becomes a billing trap. But they remain perfectly useful for teaching fundamental loop logic or for just handling tiny inputs under maybe 100 elements. Because they're so easy to implement, they're the perfect training wheels for programmers to practice on.
Comparing bubble sort and selection sort side by side, we see bubble sort works through brute force neighborly swaps. It repeatedly steps through the list, compares adjacent items, and essentially bubbles the largest unsorted element to the top. Selection sort is a bit smarter. It scans the whole unsorted region first to find the absolute minimum, and then swaps it into place. Both are terrible for large data, taking n squared time, but selection sort usually performs far fewer physical swaps in memory.
But bubble sort actually has one major advantage over selection sort. It is a stable algorithm. This means equal elements perfectly maintain their original relative order during a sort. So if you have 2 items with the exact same value, a stable algorithm guarantees that whichever one came first in your original unsorted list will still come first in your final sorted list. Bubble sort does this naturally. Selection sort, however, due to its long-distance swapping, does not.
Section 3. Linear speed. Insertion sort.
Let's look at insertion sort, which really acts as the ultimate cleanup crew. Its inner loop terminates early upon hitting sorted elements, achieving lightning-fast linear time based entirely on the lack of inversions. Unlike bubble or selection sort, insertion sort scans backward through already sorted data to find a home for the current element. If the data is already mostly in order, that inner loop just stops immediately. In the absolute best case, it achieves O of n linear time. That means it's incredibly efficient for lists that just need a tiny bit of tidying up.
Section 4. Heavyweights. Quicksort versus merge.
When we graduate to massive, randomized datasets, we need the heavyweights. Quicksort and merge sort take entirely opposite philosophies. Quicksort does all its heavy lifting during the dividing step, whereas merge sort does its heavy work combining the lists back together. Think about it. Merge sort simply splits the data evenly down the middle until it hits single items. That's a trivial divide step. Then it carefully interleaves them back together. Quicksort, on the flip side, picks a pivot point and aggressively partitions the data around that pivot. By the time the divide step is done, the combining step is basically non-existent.
Quicksort has a highly efficient inner loop that makes it blazingly fast in practice, typically 2 to 3 times faster than merge sort. But there is a catch. A poorly chosen pivot can actually degrade its performance all the way down to worst-case quadratic time. That's the primary risk here. It expects to hit that sweet spot of O of n log n time, which easily dominates n squared. But if you continually pick the worst possible pivot point, its performance just absolutely plummets.
Section 5. Space and memory trade-offs.
So, if quicksort is risky, why not just use merge sort since it guarantees safe expected time in all cases? The crucial question is, why wouldn't we just use it for every single algorithm we write? It gives us the predictable big theta mathematical guarantee of optimal time, and it's stable. It sounds perfect, right? But as always in engineering, there is a trade-off.
The catch is the memory tax. Bottom-up merge sort needs an entire temporary auxiliary array exactly the same size as the input. This is not an in-place sort. While quicksort requires virtually no extra memory to shift items around, merge sort requires big theta of n extra space just to hold the elements while it interleaves them back together during that intense combine step. In a modern cloud context, paying for 1 million extra memory cells just for temporary storage forces engineers to look for space-saving alternatives. Think about it. If you're processing 1 billion records, merge sort requires you to provision enough server RAM to hold a second, entirely empty array of 1 billion records. That kind of memory overhead is simply unacceptable in strictly limited hardware environments.
And this brilliantly illustrates why you might pivot to heap sort. It's an in-place alternative that guarantees efficient time while using almost zero extra memory. Heap sort really gives you the best of both worlds when it comes to worst-case guarantees. It provides the O of n log n time efficiency of merge sort, but achieves it with the O of 1 constant space efficiency of selection sort. When memory is at an absolute premium, but you still need guaranteed speed, heap sort is your answer.
Section 6. The ultimate sorting cheat sheet.
To wrap up this masterclass, let's consolidate our engineer's toolkit. This matrix perfectly summarizes the time, space, and stability trade-offs of every single algorithm we've explored today. You can see bubble and selection sorts sitting there with their slow n-squared times. You can see insertion sort's potential for linear speed. And among the heavyweights, you can clearly contrast quicksort's in-place speed against merge sort's memory tax and heap sort's perfectly balanced compromise. As we conclude this explainer, I'll leave you with this fundamental engineering challenge to ponder the next time you write a line of code. When should you sacrifice processing time to save physical memory space in the real world? Because remember, there's no such thing as a perfect algorithm, only the right algorithm for your specific constraints. Are you optimizing for a fast inner loop, minimizing cloud memory usage, or ensuring equal elements stay absolutely stable? The choice is yours.